So the second part of chapter 13 is about liquids. We need to talk about boiling points and vapor pressure. So here we go. You probably haven't been to a volcano, but you've probably seen pictures like this of melted rock, kind of crazy. It would be fun to go to a volcano. Anyway, substances that flow are called fluids. So whether it's a liquid like the left or a gas, as in the right, they're both fluids. So liquid, gas, liquid state, gaseous state, they all are grouped under fluids. The properties of a liquid are going to be determined by those intermolecular forces and how much motion the particles have. Those are the two things that make something from a solid into a liquid. Evaporation is taking a liquid and making it a vapor, a gas. If it happens at a temperature below the boiling point, it's called evaporation. And so you know that you can hang towels out to dry, puddles evaporate away. So if you have an open system like this forest area, this water could vaporize away. If you had a container that was open, some of those water molecules would go shooting out of the opening, and eventually it would vaporize away and evaporate. There has to be a certain amount of energy that those particles have in order for them to become a gas. They have to be moving faster, fast enough to overcome those attractive forces. And so, interestingly, when things evaporate, the remaining liquids are going to be cooler, and that's why it feels good on a hot day to mist yourself and fan yourself, because that evaporation process, the fast-moving water molecules leave, the slower ones, the cooler ones, stay on the surface of your skin. This is a terrible graphic, I apologize, but it's what I've got. Vapor pressure is how much force that substance's gas creates, and it's really more important in a closed container, but as you go from liquid to gas, that's evaporation. As you go from gas back to liquid, that's condensation. And the particles that are going off, flying off as gas, are creating pressure. And if there's a constant vapor pressure, closed system, there's going to be some things going out of solution, becoming gas, and some things coming from gas back to solution or liquid. Equilibrium is another important concept, where there's just back and forth, like a teeter-totter balance. The rate of evaporation and the rate of condensation, when that becomes equalized, then you're at equilibrium. And that's only going to happen in a closed system. So this is a little terrarium. There's somebody who's had a terrarium where he's never put water in for 25 years or something. You can look them up on the internet. But basically there's a certain amount of water. It vaporizes, it recondenses. Evaporate, recondense. Evaporate, recondense. The same water molecules can sustain things in a terrarium. And they will be at equilibrium. I'm going to skip this right now. So, vapor pressure and temperature change. If you increase the temperature, you're increasing kinetic energy. You're going to increase the number of gas molecules, which means you're going to increase vapor pressure. Warming at the liquid makes those particles move fast. More of them are going to have the ability to escape at the surface. These are kilopascals, vapor pressure in kilopascals. Remember, that's our unit of pressure. For different substances at different temperatures. So 0 degrees, that's solid water. It still exerts a vapor pressure. It's kind of weird. So in your freezer, you probably noticed crystals forming inside of packages, freezer burn. That happens because some of the water that's in your food, it solidifies, but then it becomes a gas. It'll actually sublime. And if you get to the bottom, especially at the end of the winter, of your ice cube tray, sometimes you might find some weird looking ice cubes. That's because some of the water molecules, even in frozen water, some of those water molecules can escape and make a gas. And then they get out in the bag and go, oh my gosh, it's cold out here, and recrystallize. But different temperatures, different pressures, okay? Manometers are another way, in addition to a barometer, to measure pressure. And it's a similar idea. This time the mercury is in the U part of the this little glass tubing. We used to use this a lot more. Don't tend to in high school chemistry anymore, but if you warm up a substance, some of it's liquid, some of that will become gas. The warmer it is, the more pressure it will exert. So this is at 0 degrees, this is at 20 degrees. More ethanol molecules in the tube pushing harder on the mercury pushes the mercury up the arm, and that difference is measured in millimeters, but then changed to kilopascals. This is how they used to have to measure things. So here's a small difference from where the molecules are hitting the surface of the mercury and where the mercury hits the pressure here. All right, boiling. This is a really big deal. Most people don't get this. Everybody thinks boiling is at a specific temperature. It's not just temperature, okay? Boiling happens when enough of the particles have enough kinetic energy to vaporize. So when you watch a pot of boiling water, you're actually seeing those bubbles that are in there aren't air bubbles, they're gaseous water bubbles. And those are escaping from the surface of the liquid when it bubbles at the surface. Boiling point is the temperature at which the vapor pressure of the liquid is equal to the external pressure, the atmospheric pressure of the liquid. And that's a big deal. So how hard the air is pushing down versus how hard the water liquid pressure is pushing up. When they get to the same pressure, the substance will boil. And so liquids boil when vapor pressure is equal to external pressure, which means on different days at different elevations, you're going to have different temperatures when something's boiling. If you have a low external pressure, like if you go up on the pass, anybody been on camping, backpacking, you go up to cook stuff, it takes forever to cook it. Why? Well, because you're hungry, for one, after backpacking, but for two, the higher elevations, lower atmospheric pressure, the water boils sooner. It's at a lower temperature. The food has to be at a higher temperature to cook. Okay, if you have a high external pressure, like a pressure cooker, the boiling point increases, and that's why back in the old days, to cook a roast or something, people would put them in a pressure cooker to keep the moisture in it. So again, elevation or altitude and boiling point. Normal atmosphere, sea level. This is mean sea level. Of course, sea level changes, right, during the day, but anyway, that's another story. But the surface pressure is 101.3. Surface pressure, when it gets to be the same as that 101.3 for water, that happens at 100 degrees at sea level. Okay? But if you go up to Mount Everest, there's only 34 kilopascals, and water will boil at 70 degrees. Okay? So same appearance, boiling, different temperatures by a lot. And why? Because the pressure is so much different. Just an aside, you've probably seen on cake mixes and things about baking at elevation. Denver has probably the largest population in the United States of people living at 5,000 feet or so above sea level, and so you do have to adjust your cooking when you're trying to bake things. It does change. These are some vapor pressures of different liquids and how they change at a time. Of course, most of us, the only thing we ever see going from solid to boiling is water, and most of us don't deal with these other things. So, since a liquid can have various boiling points depending on the pressure, you've got to have a standardized point, and that is at a pressure of 101.325 kilopascals, or 1 atmosphere. Each of these liquids boil at a lower temperature than water, but we can make them boil at a higher temperature if we increase the pressure. And I'll do a little demo on boiling water with an ice cube, hopefully for you. That's it for today.